Hi guys, welcome back. So we are still busy with some Euclidean geometry, specifically similarity, right? Now, there's a concept that you've been using almost ever since you started doing your geometry, and this is the Theorem of Pythagoras. So now we're going to try and use some similarity to prove the Theorem of Pythagoras, just so that you can see exactly where does this come from. Because I know we've been saying to you the square of this is equals to the square of that plus the square of that, but what exactly is this? Where exactly does it come from? That's what we're going to try and do right now. So let me just take you through that, and then we can see if we can look at exactly where do we take this from. So here, this is still our mind map of what we've been looking at so far. Now, the Theorem of Pythagoras, you know that the condition is it must be in a right-angled triangle, right? The square of the hypotenuse side is normally equal to the sum of the squares of the other two sides. And your reason is normally just Pythagoras, right? And mathematically, you know that the hypotenuse side, we normally use it as r. So r squared is equals to x squared plus y squared. That's what the Theorem of Pythagoras says, right? When you talk about the sum of the squares of the other two sides. Now, to prove this, the first thing that you need to do, so because this is a formal proof, you start with a construction. And the construction will be to draw a line from the vertex where the 90 degrees is, so that this line intersects with the hypotenuse at 90 as well. So there must be a perpendicular relationship between the line that you are constructing. Now, this will look like this, right? So you draw from vertex C or to the line AB such that it is perpendicular to that line, right? And then the condition here will then be, we then need to try and prove that this triangle AEC, is similar to the bigger triangle, which is ABC. And also prove that the triangle ECB is similar to the bigger triangle ABC, right? So what am I trying to say? The first condition is to prove that AEC, right, is similar. So similar is normally the horizontal, the vertical lines. You remember that, the three vertical lines is similar to the triangle A, because E is a 90, it must go with CB like that, right? So I must prove these two, number one. And then number two, I must then prove that the triangle EC with the B, it must also be similar to the other, might not really be the same, but the concept is what we're trying to look at. Triangle CAB, right? So it must really be that these two triangles are similar to each other. From this, we'll then look at what we can do. Remember, to prove similarity, we either use sides in proportion or we use equiangular, right? So I will then say in triangle AEC and triangle, so I'm just going to label them first so that we have a focus, ABC. I know that the angle A is common, so angle A is common, and I know that the angle AEC is equal to the angle ACB, which is equal to 90 degrees. Remember, that was the condition of you constructing the line. Automatically, because the two angles are equal, it makes the third angle to be equal because of the sum of angles of a triangle. So that makes the angle ACE to be equal to the angle B, right? I will just say it's angle B. And my reason for this will just be remaining angles of a triangle. Therefore, you can claim that the triangle AEC is similar to triangle. So A is A, right? It goes with the other angle at A, and then C, B like this, right? And my reason here will be equiangular. Equiangular. Remember, you do write your reason, equiangular, because we've proven that the angles are equal. And then because of this, we then look at another triangle, right? Or another pair of triangles, which will be this one here, my BCE, and the bigger triangle again. So I will start by labeling it again. In triangle ECB, guys, I really hope you are following me here, because I can see that it's quite a lot of things that I'm writing here, but please do try to follow me as much as you can. If you can't, just write it down so that you can go over it again after we are done here. A, B, C. Now, I will then look at these two triangles. I can see my angle B is common, so I will say angle B is common. Already I know that. Angle B is common. And then there's a 90 degrees in both the triangles, right? So that will make it BEC, which is equals to ACB, and this is equal to 90 degrees. Then you know the third angle will be equal, and the third angle, according to the two triangles, it will then be ECB, which will then be equals to the angle A, and my reason will be remaining angles. And then you can claim that the two triangles are equiangular as well, right? So I'm going to write them down this side. The first pair that I proved to be equiangular was AEC and ACB. So triangle AEC, we said it was similar to triangle ACB. And then the second one that we proved was BEC, which was similar to BCA. Triangle BEC, which was similar to triangle BCA. Good. Then we're going to use this to then show that the square of the longer side is equal to the sum of the other squares. Now, guys, the theorem of Pythagoras is one very important tool to try and find an unknown side when we are given the other two sides, right? Or when we then start talking about the concept of circles, you will see that to find the radius and all of that, we use this concept. But it is a very important concept. So now what we're going to do, we're going to link one side, that is the hypotenuse side, on one triangle, and link it to the other side, which is the hypotenuse side on the other triangle, and see whether we can then find some similarities there in terms of the ratio. So, in the first scenario, which is number one, so I will call it number one, I know that if I have AC over, so AC, it must go with, in the very same triangle that I have, because I'm trying to look at the side AE, right? So I will make it move with the AE there. So that will be AE. Then it must be equals to, because I took the last ones there, it must go with the AC there, right? So AB will be the hypotenuse side, so that's AB over AC. If I simplify this, it will then give me AC squared is equals to AE multiplied by AB. I leave it there. This becomes like my equation number one. And then I go to the second scenario that we spoke about of similar triangles. Now I will say if I want the hypotenuse side of BEC, the hypotenuse side of BEC will be BC. So BC must go with BA. Because I want to link it with the longer side of the bigger triangle, which is AB. I will link it with EB, and this will link with BC. So it will therefore be BC over BE is equal to BA over BC. And then also I cross multiply here. It becomes BC squared is equals to BE multiplied by BA. Now you can already see that if I was to add these two, then there will be some similarities that I'm going to find there, right? So let me just show you what I mean. I'm going to say, if I can say AC squared plus BC squared, let me show you on the diagram. The AC squared will be the B there, the small letter B, plus the BC squared will be the small letter A. It must be equal to this one here, which is the small letter C, according to the theorem of Pythagoras. So that's what I'm trying to find there. So this will be equals to, that is AE multiplied by AB plus BE multiplied by BA. And then you know, guys, there's AB there. I can take it out as a common factor. So that's AB into AE multiplied, BE. If I add my AE and BE, it will give me the whole of AB. So now I land with AC squared plus BC squared is equals to AB into AE, remember, plus EB. And I said to you, what is inside the bracket, if I add it, it gives me AB. So this becomes AB multiplied by AB, and it will therefore give me AB squared. So this will be AC squared plus BC squared, AC squared plus BC squared. And then if we use the small letters, the small letter for AC is B, the small letter for CB is A. So this is B squared plus this is A squared, which will then be equals to C squared. And that's how you then prove your theorem of Pythagoras. So I do know that all of this just looks like it's a lot of work that you need to do, but it's mainly just for you to know where the theorem of Pythagoras comes from. Guys, I can already see your faces there. You are thinking, yo, what is this man trying to say? But honestly, if you wrote it down and you go back and re-look at it, I promise you, you are going to get it. And then just try to see, what is the concept here? The concept is proving the smaller triangle with the bigger triangle, that they are similar. Another small triangle with the bigger triangle, that they are similar. And then link those so that you can try and prove the theorem of Pythagoras. I promise you, it's really going to work. But because I've really been doing a lot of talking here, let me just give you a quick ad break and I'll be back with some more. So please stay tuned.